Okay folks, so in the last video we looked at an introduction to what we meant by linear transformation. And essentially we said, okay, we've got a linear transformation if we have a way of mapping from one space to another space so that the linear transformation itself distributes over whatever we mean by addition in those two spaces, and if constant multiples can be factored out, scalar multiples can be factored out. Whatever we mean by that sort of scalar multiplication. So let's look at a few more examples now. And we're going to introduce some some spaces that we'll be talking about throughout this course. We might as well spend a little bit of time on this now. So let's consider the set of all functions which are differentiable on the real line and whose derivatives are themselves continuous. Continuous, however you want to fill in that blank. So remember that if a function is differentiable, it's also continuous. But that doesn't necessarily mean that the derivative of the function is going to be continuous. And if you're interested in finding some examples of functions that are differentiable everywhere but those derivatives are not continuous, let me know. So we're going to denote this space of functions. So of all the functions out there, the ones who are differentiable and their derivatives are continuous, we're going to call C1. Okay. Likewise, we'll let Cn denote the space of all functions that are, first of all, n times differentiable and whose nth derivative is continuous on the real line. Finally, we're going to use the notion C0 to denote the space of all functions that are just continuous on the real line. So notice that if I've got a function that's 3 times differentiable, it's also if it's C3, it's also C1, and it's also C0. In fact, we say that the C3 functions are a subset. You could use the word subspace if you wanted to, of the functions that are twice differentiable, of the functions that are once differentiable, of the functions that are themselves just continuous. So that's some weighty notation. Let's talk about it right here. The function f of x equals x cubed is not C1 on f. Even though the cube root function is continuous, its derivative does not exist at x equals 0. So f of x equals the cube root of x is not C1, even though it is C0, meaning its derivative does not exist at x equals 0. F prime of x is equal to 1 over the cube root of x squared, and this is undefined at x equals 0. So we're not continuously differentiable on the real line, even though we are a continuous function. Okay. The function g of x equals x squared is C1, since its derivative g prime of x is 2x, and that exists for all real numbers. Actually, in fact, we could say that g of x equals x squared is actually C2 because its second derivative exists and is continuous. And further, we could even say that it's what we call C infinity, meaning that I can take its derivative countable number of times, and I'm always going to get something that's continuous. Specifically, when I take the third derivative, notice I get 0, which is continuous on the entire real line. Same thing if I took the fourth derivative, I get 0, which is continuous on the real line, and I can repeat this as often as I wish. So in fact, it turns out that a polynomial like x squared is what we call C infinity, meaning it is differentiable a countable number of times.